Okay, let me zoom in. It says, answer the following questions in terms of principles of chemical bonding and intermolecular forces. In each explanation where a comparison is to be made, a complete answer must include discussion of both substances. The following complete Lewis electron dot diagrams may be useful in answering parts of this question. So, question A. At 1 atmosphere and 298 Kelvin, pentane is a liquid, whereas propane is a gas. So this one is a liquid at those conditions. Oops, and this one is a gas. We might have done this question way back. So how would you justify? You have to mention both pentane and propane, and you have to use the word intermolecular force or IMF somewhere. So what would you say?
One has the higher boiling point.
Yep. So why does say let's see, pentane is a liquid, so it's got a higher boiling point. Higher.
Is it because the intermolecular forces are stronger?
Correct. So you say pentane has stronger IMFs than propane because why?
Because it's a liquid.
So a
propane's a gas?
liquid is evidence. That's evidence of it. But why would it be a liquid? Because it's why?
Because it is bigger.
Yep, it's a
That
larger
Really?
molecule.
And that makes it stronger
So
intermolecular
yeah, but
forces.
specifically, you guys got to look at it. Which of the three intermolecular forces are dominant for pentane and propane?
Hydrogen bonds.
Hydrogen bonds review have to have an OH, an FH,
OH,
or an
NH.
NH. So it can't be hydrogen bond.
Okay.
Oh god, that would be is it the one where it shifts
Yep,
electrons to one side? I
Yep.
forget what it's called. Is it the London London dispersion forces?
yep. So London dispersion forces are stronger. Okay, London dispersion forces again they're the dominant force for nonpolar molecules. How do I know that pentane and propane are nonpolar?
They're completely symmetric.
They're completely symmetric and they contain only C's and H's. To be polar with these types of molecules, you have to have asymmetric, typically oxygens or nitrogens. And so since these don't have any oxygens anywhere, they are completely nonpolar. And since pentane has an extra carbon, so it's a little bigger, it can have stronger London dispersion forces. Okay, and that makes it essentially stickier to itself. So it has strong enough forces that it'll stay as a liquid, versus propane doesn't have strong enough London dispersion forces, so the kinetic energy turns it into a gas. Okay, B, why is methanol a liquid but propane a gas? So this is a little different. Methanol versus propane. Here, I'll switch over to blue. What's different about methanol and propane?
Methanol has the OH.
Yep. So this one is London dispersion forces. It is polar, so it has dipole-dipole. And it also is capable of hydrogen bonding because it has an OH group, which these collectively make it very strong intermolecular forces, versus this one is weak because it only has London dispersion force. So you could just say the presence of an OH group makes hydrogen bonding, because that's the really special one, makes hydrogen bonding possible, therefore its intermolecular forces are strong. So methanol has strong intermolecular forces due to hydrogen bonds. Okay, and then let's see, C, indicate the hybridization of the carbon atom in each of the following in methanol. So I'm going to erase my blue, so we're looking at this one right now. There's only one carbon in methanol. So what is the hybridization there?
sp3.
Correct.
Yeah.
Because you look at it, there's 1, 2, 3, 4 things around it. Okay. And if they asked, I'm just throwing out review every time. Sorry, this gets old. If they asked bond angle,
Oh, the bond angle of
90 something.
109.5.
very good, Tyler. 109.5. And if they asked for geometry,
Tetrahedral.
tetrahedral. Very
Yeah.
good. Very good. Okay. So next one, methanoic acid or formic acid. So I'm going to switch to green. That would be this guy. Methanoic acid. What is its hybridization?
Is that SP3?
Nope.
two, yeah.
It's sp2. Why?
There's 3 groups of electrons.
There's 3 groups of electrons. Double bonds, when you're talking hybridization, double bonds only count as one domain. So there's a
Okay.
total of 3 domains. So that makes it sp2. If it had asked for bond angle, like say here, what would the bond angle be?
120.
120, very good. And if they ask for the geometry, what do you call 3 things spread out 120 degrees?
The tetra something.
Nope.
Darn.
120.
Planar.
That's kind of like equilateral triangle, right? And notice, would it be 3-dimensional or 2-dimensional?
3-dimensional.
No, it's 2-dimensional. Okay, so 120 makes it kind of flat. Like this is a perfectly flat molecule. So
Is it trigonal planar?
yeah, this is the trigonal planar. Trigonal planar. So it's important to note that like on methanol, it really would look something like if you could draw it, one like this, one kind of sticking out, and one kind of and then this one goes out to the next O group. Okay, so it really looks like a 3-dimensional kind of tripod, right? With a tetrahedral spacing, and then versus methanoic acid, if you had a piece of paper, see if I can draw this flat piece of paper. Oh, what in the heck? I changed it to a rectangle. Oh no.
You just hate when that happens.
All right, so if you had, here's your, oh geez, it is really trying to do stuff. If you have
It
your,
really wants to be a rectangle.
yep, I don't know why. Oh, ink to shape is on, that's why. Okay, if you have your O group sitting there, you've got your carbon here. On that paper, you would have, and I could draw it a little better. Actually, it should be out here. And that would be sitting completely, this portion of the molecule would be sitting completely flat on that sheet, right? With 120-degree bond angle all around it. So that one is a flat molecule or a trigonal planar molecule at that end of it. Okay? You guys okay with that? Yes, no? Okay, I'm gonna expand upon that. What happens if they had asked, let me erase this stuff. What happens if they had asked, hey, methanol have different hybridization around the carbons, but they have similar OH groups. What is the hybridization on the oxygen in both of those? So this oxygen and this oxygen.
Just SP.
Nope.
should be
These also,
SP3,
hey,
right?
these also count as domains.
Oh, so SP2.
SP, count them up. 1, 2, and then 2 lone pairs. So what would it be?
Wouldn't it be SP3?
SP3. So, okay, again, you count. So when you're doing hybridization, a lone pair counts as 1. A single bond, single, counts as 1. And a double counts as 1. And a triple counts as 1. So you just add up those entities. Those are all called domains. Okay, so you just count up, a domain is just the space where you would find electrons. So around this oxygen, I would potentially find electrons in 1, 2, 3, 4 spaces, and you add those up. Yep, and then you just basically name it. If it equals 4, then it's sp3. If it equals 2, like in the case of this one, right, carbon dioxide, what's the hybridization around the carbon?
SP.
sp. Okay, and so that one, because it only has 2 domains, right, that would be linear or 180 degrees. But if they had asked what's the hybridization around the oxygen, then you have to look at, then you have to look at 1, 2, 3. So what's the hybridization around that oxygen?
SP3.
Careful,
Oh.
careful, Savannah. Yep, you got to add it. So it's just sp2. Okay, so in my mind, I'd keep going back to the balloons. If you have, again, think of these as just even think of the bond as a balloon. What's the easiest way to space out 3 balloons around a central object? Well, that's got to be in some kind of a triangle. And so that triangle is called trigonal planar. And since there's only 3 balloons, 3 is sp2, so this would be the number of domains. Okay, and then this would be the hybridization. Okay, 2 was sp, 4 we said was sp3, 5 was sp3d, and 6 was sp3d2. So, yeah, and it just takes some practice. So we'll keep going through because I think the next question has more of these. Okay, how about draw the complete? We're on D. Draw the complete Lewis electron dot diagram for a molecule of propanoic acid. Propanoic acid. So propanoic acid is very similar to propane. It has the same root word. So, and it's got hydrogen, 3 carbons, right? And then it's got 5 more hydrogens and 2 oxygens. So let's see if we can do it. Oh, and it kind of looks like, I think they gave you this one, because it also looks like methanoic acid. You guys remember the whole meth, eth? We could review this. Meth, eth, prop. See if you guys, do you remember the 4
Yeah.
carbon? So meth, eth, prop, what was the name for 4?
Bute.
Bute. And then pent, and then hex, etc. So they gave us methanoic acid, and they said draw propanoic acid. So you guys, are you okay if I just take, there's the acid part, and instead of this hydrogen, I'm going to connect some additional carbons. So propanoic acid would look like carbon, 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 right? And I have a double bond O and a single bond O and an H. So there's the end, that's the oic acid part. And then I just fill in the rest with those. Okay, so that's how an organic chemist would do it, and that's how you could save time on the AP test, is by trying to think about what are called functional groups. And since the naming kind of matched, the oic acid matched from methanoic and propanoic, you could do it that way. Or if you don't know all that nomenclature, then you would just add up valence electrons and use the skeleton structure. So you would do things like, okay, hydrogen is 1, carbon is 4, hydrogen is 1, oxygen, so I have 2 oxygens, and oxygen is 6. So let's see, I have a 12 there and a 12 there, 24, 29. I think I have 30 electrons to assign. So 30, and I could just double check. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. I forgot these, 28 and 30. Okay, so I have a total of 30 electrons. Okay, so that's propanoic acid. Let me see. Part E says explain the observations about the 2 carbon-oxygen bonds in methanoate, the formate ion. Okay, you may draw electron dot diagrams of the methanoate ion as part of your explanation. and it says explain why the two carbon-oxygen bonds have the same length. Okay, so here you go. Methanoic acid, its conjugate base would be called methanoate. So can you guys tell which one of these hydrogens do you think is the acidic hydrogen? Which one do you think is easiest to pop free?
The one connected to the carbon.
The one connected to the oxygen. So hey, and you gotta this is just something that you learn with practice. The ones that are on the functional group. So usually things that are on the carbon backbone, they're not that critical. But the things that are on the functional groups, those are the ones that do stuff. So that's the hydrogen that's gonna pop up or pop off if it's an acid. And so then you've got, let me draw this in. If this pops free and you're left with methanoate, which I think is like that, and methanoate, again, you can add it up. Here's the formula, HCO2 minus. So HCO2 minus has 1 plus 4 plus 6 plus 6. So 1 plus 4 plus 12 plus, when I have a negative charge, what are you going to do?
Add one.
Add one more. So I've got 1 plus 4 plus 12 plus 1. So that would be 18, right? So then I go in and I'm going to do 18 electrons, which I think I've got, correct? Okay, and now it's asking, though, why would you consider, say, these two bonds, the single bond and the double bond, why would they be the same length? You guys have a why would those two green bonds, the double bond and the single bond, why would they be the same length?
Is it because
So would the extra okay, so normally the double bond would be shorter.
Yes, correct. Typically double bonds are shorter, but in this case they've measured it and they found that both of those bonds are the same length.
But the extra lone pair would
Yeah, it actually has to do with this. It has to do with this guy. What could potentially happen to that blue set of bonding electrons?
Oh, it could just move to the other.
It could move to the other
they're
one.
1.5 bonds.
Yeah, so this is called, there's a name for it, and you'll get credit if you mention this word. So let me draw this in here. Oops. Okay, so, and I guess you're right, Arthur, like these kind of migrate here as well. So, like basically all that whole end of the molecule, the whole right side of the molecule, it's just a bunch of electrons. Okay, again, why would electrons want to stay towards the right hand side of that molecule? Can you guys decipher? What's present there?
Oxygen.
Oxygen, and so why is that important?
That's very electronegative.
It's very electronegative, okay? So, because of the structure of the oxygens, you just get a glom of electrons. Those glom of electrons are free to move, and this is called resonance. They're called delocalized electrons. Okay, and
they just like to party.
Yeah, exactly. And so this is a form of resonance, and Arthur already mentioned that the double bond and the single bond are actually two 1.5 bonds. Okay, because you average them out. There's 3 sets of bonding electrons, a double and a single, but there's only 2 regions, right? There's a region there and a region there. And those 2 regions can share 6 electrons, so we call them 1.5 bonds. But if you just said resonance structures exist, so the bonds are the same length, that would give you credit. If you use the word resonance or 1.5 bond or delocalized electrons, then you would get credit. Okay. Do you guys remember? Here's some here's some nomenclature for you. Do you guys remember the other name for a single bond?
I remember there was pi bonds and
there's this one.
No, I don't know.
See if you guys okay. And again, I'm jogging your memory because again, this is like warm up. We're doing warm ups right now.
Sideways B bond.
It's not omega, is it?
Yeah, it's not omega. Close.
Sigma.
Oh, sigma.
It's a sigma bond. Okay, so a sigma bond is a single bond, and they are what they're called. It's basically a linear overlap of electrons. So carbon had some hybridized electrons, oxygen had some hybridized electrons. You get a linear overlap, and that's called a sigma bond. Now in this bond right here, you guys remember a double bond, what type of electrons or how are those electrons actually holding those together? Do you remember the two types there?
Mm,
And Arthur already said it.
Is it pi bond?
Yeah. So hey,
Oh,
you
yeah.
have these electrons basically overlapping. That's the sigma bond. Okay. And then the second set of electrons, these are delocalized. Okay. Over the sigma bond. So basically, it's not like you got 4 electrons all in the same spot. It's like 2 of the electrons are directly in between the C and the O. So let's see if I can draw this. C, O. Here's 2 electrons, and they zoom everywhere in this yellow region. And then the pi bond actually, here's some more hybridized orbitals with electrons in them. They form, I'll use my rainbow pen. They form this space and this space. Okay, this is together 1 pi bond. Okay, so the sigma bond is the yellow region that's directly between the 2 atoms, and then the pi bond is kind of these electrons that hang out above and below the sigma bond and basically add strength. They just hold because you've got more electrons trying to be shared in 2 spots, then you just got a stronger bond. Is that okay? And then how
yeah,
about
makes sense.
yeah, how about this one? Because this is one that always shows up. This is welding gas acetylene. Okay, and so this would be a triple bond, right? But it's really comprised of what?
A sigma and a pi bond.
Yeah, except it's a triple. So 1 sigma
2 pi.
and 2 pi bonds. Okay. So that one, if I drew my little structure, it would look like a yellow. Okay, there's a sigma bond. Then you'd have a pi bond. Let's see if I can draw this. Okay, imagine you have a pi bond from like here to here, and then a pi bond from like, well, actually, okay, it would be like pi bond. There's 1 pi bond, okay, above and below, and then behind and in front.
Oh, like on all 4 sides.
Yeah, on all 4 sides, you'd have basically electrons. So what this makes is like a little barrel of electrons around the carbon, around and in between the carbon. So there's 6
electrons. Super strong.
Yeah, this represents 6 electrons, but those 6 electrons are just basically spread out in between the 2, and they're very, very strong, and they're very, very short bonds. So the distance from here to here would be a small gap, right? Okay. I'm gonna keep going because it's Friday.
So is that why they're shorter? Because they're
think of them like rubber bands. They're just tighter. It's like it's just like something that hasn't been stretched out, and it's basically got extra wraps of bungee cord around it, so it can't move apart. So they don't stretch.
Okay.
However, when you do break them, they release a lot of energy. Okay. Let's see. Number EII. The length of the carbon-oxygen bonds in the methanoic ion is intermediate between the length of a carbon-oxygen bond in methanol and the carbon-oxygen bond in methanol. Oh, so I think that's asking about intermediate bonds. Oh yeah, so let me erase stuff. So again, just they said why is the length Why is the length somewhere in between this length and this length? And we know that those bonds really behave, okay, in our methanoate, they really behave as 1.5 bonds. So whenever there's resonance, whenever you get something where the electrons can move, then you get basically a bond that's called bond order. You get a bond order between single and double. Okay? Or you could look at something like this one, nitrate. I'll just draw it for you so we don't waste a lot of time. Right? So that one, how many different locations could you move the double bond to?
2 other ones.
Yeah,
well,
2
3
other
total.
ones, 3 total. So what you'd say is there's 2, 4, 6, 8. There's 8 electrons, or you could say 4 bonds spread across 3 domains. And you could say that that's 1.33 bond. So it's basically a little bit closer to a single bond than a double bond. Does that make sense? So those 3 yellow,
Yeah.
or sorry, the 3 yellow regions would actually, this region, and this region, they'd all be the same bond distance, and they would be a little bit shorter than a single bond.
Oh, okay.
Okay, because they really behave like 1.33 bonds. Okay.
Got it.
Okay. Moving on. I got one more question. It is 10:59. So I know if you guys have to go, take off, but I want to cover one more. Where did I put it? Right here. And I'll try and just be more straightforward. I won't do as much review. So if you have to, I am going to post this video if I go too fast. Okay, it says answer the following questions. It says about molecular behavior and chemical concepts. The structure of glucose and cyclohexane are shown below. Identify the type of intermolecular forces in both glucose and cyclohexane. So, looking at glucose, what of the 3 IMFs are you going to write there? You can write one of them, 2 of them, or all of them. What ones are present?
Well, there's OH, so
Correct?
hydrogen bonding.
Yep, H bond.
And there's a CH2OH top, so is it
Yeah,
dipole?
that definitely makes it non-symmetric. So then if it's non-symmetric, then dipole. And you're always gonna put London dispersion force because every chemical compound has electrons.
Okay.
Okay, so everything has London dispersion force. Now, out of those 3, which one is gonna be the dominant force or the most important to glucose?
Hydrogen bond.
Correct. The strongest one is gonna be the dominant force, and that's the one that influences its behavior. But
Okay.
for this question, it's just all 3. Okay, and then how about for cyclohexane?
Just London dispersion force.
Correct, because it's not polar.
Yeah.
All right. Okay, glucose is soluble in water, but cyclohexane is not soluble in water. Explain. This one is H2O soluble.
I know why.
Okay, why?
That's because that molecule is nonpolar and so is H2O.
Correct. This one is polar. So H2O and
Yes, sorry, polar.
oh, and this one's asking, yeah, H2O and glucose. And glucose are polar. So they dissolve. And this was the like dissolves like.
Oh yeah.
Okay.
That makes sense.
So yeah, polar things dissolve in polar solvents. Okay, consider the two processes represented below. Okay, it says H2O liquid to H2O gas, and it has an enthalpy of positive 44 kilojoules per mole. And this one says H2O liquid, and it looks like you are breaking it down into hydrogen and oxygen, also positive 286 kilojoules per mole. Okay, for each of the two processes, identify the types of intermolecular or intramolecular attractive forces that must be overcome for the processes to occur. So intermolecular forces, those are the ones that we just listed above. Intramolecular forces, what's another name for intramolecular force?
Outer molecular forces.
Mm,
You guys get
Oh,
that?
I know.
isn't that the charge? No.
It's, hey, look
Bonds?
down here. Intra means within. So what holds atoms together inside of a molecule?
The bond?
The bonds. Okay, so intramolecular means the bonds inside of a molecule, and intermolecular forces mean the attractive forces between two different molecules.
Okay.
Okay, so what's happening in process number 1? What are you doing to water?
Vaporizing it.
So, is that a physical or chemical change?
That's a physical
That's
change.
a physical change. So, it's still water. Do you guys see it's water before and water after? It's just a different state.
Yeah.
So, if that's a physical change, are you messing with inter or intra molecular forces?
Inter.
You're doing inter. So process 1, you would say it's intermolecular forces. So I would say for I, you're breaking H bonds between H2O molecules. Okay, that's process number 1. Okay, and then process number 2, what are you doing to the water molecules in process number 2?
You're breaking the bonds.
Correct. So you're breaking
The
OH. Yep, you're breaking OH bonds inside of a water molecule. That makes sense?
Yeah.
Mm-hmm.
So chemical changes, they mess with bonds, and that is intra. And then physical changes, when you're pulling things apart, molecules apart, that's intermolecular forces you're breaking. Okay. Number 2, indicate whether you agree or disagree with the statement in the box below. Support your answer with a short explanation. So the box says when water boils, H2O molecules break apart to form hydrogen molecules and oxygen molecules.
Disagree.
When you boil water, yep, you disagree. What are you doing?
You're just breaking the intermolecular forces.
Correct.
It's still water, but
Correct.
it's...
And the big thing, what's true about the particle spacing between a liquid and a gas?
They're
It's
just spread
much
out.
larger.
Yes, it's much larger. Like it's about, I think, gas like steam is 1,000 times less dense than liquid water. So you would just say vaporization breaks IMFs and spreads out molecules. Okay, so when you vaporize something, there's no broken bonds. You're not breaking any chemical bonds. You're just spreading out molecules. All right, here you go. Last part. It says, consider the 4 reaction energy profile diagrams below. Identify the 2 diagrams that could represent a catalyzed and uncatalyzed reaction pathway for the same reaction. Indicate which of the 2 diagrams represents the catalyzed reaction pathway for the reaction. So, identify 2 diagrams that could represent a catalyzed and uncatalyzed reaction pathway for the same reaction. So, same reaction, that tells me the starting and the ending place have to be the same, right? They have to have the same enthalpy. So, which one has the same enthalpy change?
Wouldn't that be 1 and 2?
It looks like 1 and 2 to me. I agree.
Yeah.
Okay, those are the same. Now, which one has been catalyzed, and how could you justify?
Number 1.
Correct. How do you know that number 1 is the catalyzed reaction?
It's
Does it went
activation.
faster?
It not anything with speed yet, but it will impact speed. But activation energy is critical. So Keaton, what did you say about activation energy?
The activation energy is lower.
Correct. So that one, right? The hump compared to this one. The blue one has a larger hump, and that's due to the fact that you don't have a catalyst. So,
Oh, okay,
so
yeah.
you could say lower activation energy means that it's been catalyzed. Okay, and then last part, it says indicate whether you agree or disagree. Support your answer with a short explanation, and I think this is what Savannah you were getting to. Adding a catalyst reaction to a reaction mixture adds energy, and it causes the reaction to proceed more quickly.
Yeah.
True or false? It does go more quickly, but there's a problem. What does a catalyst
False.
actually do? So Tyler, why is it false? What part of it's false?
It's not like adding energy.
Yep.
It's just helping the particles find each other. Or
Correct.
whatever.
Correct. Catalysts help orient molecules and lower the activation energy. So they don't add energy. Okay. Now, what would be something you could do to actually add energy to molecules?
Speed it up.
Yeah, how would you physically speed them up? What do you do to something to speed it up?
Heat it up.
Heat it up. So if it had been replaced with this, like if they said make it true, you could say adding heat. So that's correct. Adding heat will make a reaction proceed more quickly because you're adding energy and you're basically making the particles more capable of getting over the barrier. Okay? So heat is an addition of energy. Catalyst is an efficiency thing. Catalyst just efficiently orient particles so that the activation energy is lower.
So, to answer this question, could you both have said false, like your answer, and also say just false heat?
I think they're looking for the fact that catalysts they don't affect the energy of, like, they don't affect the starting state, they don't affect this or this. All they affect is the size of the hump. That's what they're looking for. It doesn't have to do with the addition of energy. So
Yeah.
I think if you mentioned heat, maybe a good grader would catch that, but I think that would be like a secondary answer. So I would definitely, the straightforward one would just be say catalysts only affect the hump. It doesn't add energy to the reactants.
Yeah.
Okay.
Okay. Let's see. I'm gonna hang around with Keaton, and we're gonna mess around. I'm just curious, Keaton, if you could share your screen, and then we could try. I want to see what your phone says when you plug it in. Other than that, I'll see you guys Monday at 10:30. And hey, check your email. Look at College Board. See if you can find how they're gonna deliver the practice exam to you. I'm sure it's gonna be a link, and I just don't know if the link is gonna come via email or be posted on their webpage. So find that out Monday morning, and I'll see you guys at 10:30.
Got it.
All right. All right. Bye. Okay, Keaton. Yeah. So let me stop sharing my screen.
All right.
How do I get here? Stop presenting.
There we
Okay.
go.
Okay. Now you try presenting.
Screen 1. Is it sharing?
Not quite yet.
Okay. Strange. Yeah, it's not doing it. And now the present button is grayed out. Excuse me?
Hold on. Let me click something different.
Yeah, you might have it so I can't.
No, I don't think so. Let me click settings.
Yeah, it's weird. For some reason, I can't.
Nope.
Yeah. Yeah, the present, like, the button is now grayed out after I select what screen I wanted to present.
Here. Leave the meeting. Come back in.
Okay.
All right, and then try one more share screen. We'll see what happens.
Present your entire screen, a window, a Chrome tab. So I'd probably just want your entire screen.
Entire window. Then you do have to click. You do have to click like the entire window thing, and then hit OK.
Yeah. Screen, then share.
Yeah. Nothing.
All right. Nothing.
Okay. Hey. And now it's still grayed out.
Yeah, I can't even click anymore.
Here, weird. Minimize your Chrome. Is there a pop up behind it?
Nope. There's nothing.
Weird. Okay. Hey, try one more time. Leave the meeting. Come back in, and this time try sharing just your Chrome window. I'm just curious to see if that works. Okay, let's see. No luck.
Okay, yeah, that's kind of broken. I clicked on the present button when you would like join the meeting, so I could just present when I
Yeah,
came in here.
and it didn't work.
It just kind of broke.
Maybe the school district they might have disabled screen sharing of students, which might be smart.
Well, here's the thing, though. I remember that Tyler was able to do it.
Well, but hey, that they've just been changing Google Meet. Like Google Meet has done a lot of updates to itself, and then the school district might be locking things down. My guess is the school district disabled that, so students can't share their screen.
Well, also a while ago, I remember when we were trying to screen share, I tried to present once,
Yeah.
and it did the exact same thing, which is very strange.
Weird.
So I don't know. It's something with my computer.
Okay. Well, then on Monday, try the test.
Wait, if you have Discord, I can screen
No,
share there.
I don't want to use Discord, but that's okay. Don't worry about it. Just on Monday, log into the practice test. So find the link to it and then try it and see if your email solution will be timely enough and will be functional.
Okay.
And then and then we'll just report back next week.
All right. Cool.
Okay, have a good weekend.
Yeah, you too.
All right,
Bye-bye.
bye.